Hey guys, BuildZoid here, and today we're going to be taking a look at the PCB of the EVGA Z590 Dark motherboard. This board was sent to me by EVGA, so big thank you to them for providing the review sample. And since this is an extremely overclocking focused motherboard with a lot of features on it and stuff to talk about, we'll just get right into the overclocking features. So yeah, let's get started. So in the rear I/O, there's a clear CMOS button hiding somewhere around this area. But if you're using this motherboard as intended, and in other words, on a test bench, you've got a clear CMOS button over there. So you're going to want to use that one. You're probably going to want to use that one instead. There's probit headers over here, which is my preferred method of voltage read points on a motherboard because lots of, overclocking focused motherboards will give you voltage read points, but most of them implement them as just like solder bumps on the PCB, which you need to hold the probes on that, or you need to like solder little connectors to them, and that's super annoying. Whereas on the Z590 Dark, you basically get little headers that plug into that, and then those have sockets that you can actually sort of just plug your multimeter into. And then you don't have to hold the probes on solder bumps or anything. So this is super convenient. And you can check basically every voltage on the motherboard with this, or at least every important voltage on the motherboard with this. I've not actually gone ahead and checked that it can check everything. It probably can't. There's probably some minor rails for things like USB ports and audio that aren't covered, but those are features of a motherboard that I barely ever use, so I don't care. They may as well not exist. Then over here, we've got a bunch of troubleshooting LED. Actually, we've got more LEDs over here as well. But yeah, there's an array of troubleshooting LEDs. Most of them are just indicating that you have various power rails are present and outputting a voltage. Not that the voltage is in spec, just that it's present. So really, this is only useful if you're troubleshooting like a broken motherboard, as it'll make the troubleshooting process a lot faster. But under normal circumstances, you can probably just kind of ignore all of those. We've got a USB port over here for BIOS flashback functionality, a safe boot button, which EVGA's implementation of is a little bit unique. So on, say, Gigabyte, Asus, or MSI motherboards, those safe boot buttons will actually take you down to stock settings when you hit them. EVGA's safe boot button takes you to the last stable settings, at least. And the criteria for last stable settings is basically like it booted, which is not great because you can boot a lot of settings that are not really that stable. So a real issue that you can run into with this is that you can end up with like you hit the safe boot and it boots you to settings that, well, aren't safe and are too unstable to even run the BIOS. And then you're stuck in this awkward situation of like, well, I can technically get into the BIOS, but I can't change any settings in order to get the board stable enough to like actually, well, go anywhere with it. So that's the one downside to EVGA Safe Boot implementation. The upside to it is, however, if you have a very if you have a CPU that's very specific about the voltage levels that it requires to run on LN2, EVGA Safe Boot will not have any issues with it, whereas some of the, like, say, a Gigabyte or an Asus style Safe Boot, since those pull you all the way down to, like, stock voltage levels, with admittedly some, like, presets from the LN2 mode that, Asus and Gigabyte and the various other vendors implement, like, so technically, like, which basically those presets are designed that most CPUs will still boot on liquid nitrogen. The thing is, if you have a CPU that doesn't work with those presets and you hit the safe boot button on one of those boards, well, you're not booting. Whereas with this safe boot button, you would, because this will always be booting to a profile that previously already worked. The only issue is if the definition of work here is a bit loose. As in, being able to get into the BIOS is not really an indication of stability. So, yeah, this is not so much a safe boot as a last known good, or more like last postable settings. Still way better than not having a safe boot button, but that is it is just something to keep in mind with the safe boot function, is that you can technically boot settings that aren't safe on it, because it's not actually, like, it doesn't take you back down to stock. It takes you back to the last settings that worked. And when I say worked, they got into the BIOS, which not really a great criteria for working settings, but Yeah, under most circumstances, this works fine, though. Like, you know, like it is an issue that you can run into, but I'm saying you can run into it, not that it's always a problem, because it isn't always a problem. Most of the time, it's not an issue, but something to keep in mind. So yeah, then we have another clear CMOS button, which I might have mentioned that, you know, for test bench use. The dual postcodes, which actually only one of those is a postcode. The other set, the other 7-segment display is actually so that the board has a bunch of monitoring functionality. So you can track like CPU socket temperature, various voltages actually on it as well. So you can use that as a voltage display. And the thing is, well, you know, measuring a voltage with just 2 digits is kind of useless. So they added the second second 7-segment display so that if you set it to say read out a voltage, it can read out 1.35 whatever volts, or you know, whatever voltage you're measuring. If it's reading out a temperature, it can do like minus I think it goes down to minus 50 degrees Celsius, and it'll actually do like minus 50 point. So it'll actually do decimals even when measuring temperatures. So yeah, it's basically to get you a extra information readout that you can configure in the BIOS. So that's pretty neat. Then below that, we've got a power and a reset button. This is power, that's reset. They're nicely labeled over there. Oops. And then over here, we have the 24-pin at a right angle. The board is very EATX. As you can see, it didn't even fit in the photo properly. So this is where an ATX motherboard ends, and this is where the dark ends. So case compatibility is something to watch out for, but again, if you're putting it in case you're arguably using the motherboard wrong, it should really be on a test bench. And test benches don't have, well, edges. Like they're not a box, right? Like there's no limit to how wide your motherboard can be. Anyway, so right angle 24-pin, your dual CPU 8-pin power connectors over here, also at a right angle. And these are very, like having dual 8-pins is actually very useful when you're on liquid nitrogen. Though at ambient, you only really, it depends how hard you're pushing your CPU. But under most circumstances, you shouldn't even be able to max out a single 8-pin, even with like a 10900K will be just about able to max out an 8-pin. Same goes for the 11900K. So, you know, like the second 8-pin can't, like at ambient, I'd say it's debatable whether you need the second 8-pin. But if you're really if you're really pushing a 10900K or an 11900K, then I guess, yes, get the second 8-pin, plug it in. Below that, we've got more switches. So we've got triple BIOS. I'm a huge fan of dual BIOS, and triple BIOS is just one better than that. Not really in a meaningful way, because with 2 BIOS chips, you already have like, you know, recovery from bad BIOS flashes. And also you have the option to like test different BIOS updates against each other. Though I guess with 3 BIOS chips, you can have 3 different BIOS versions on your motherboard at the same time instead of just 2. Not sure why you'd actually want to do that, but you can. So that's kind of neat. Then this 5-channel dip switch over here is for enabling and disabling PCIe devices. So you can disable both PCIe. Well, this is an X8 slot, not an X16. Like there's pins in it for X16, but it's not. So, you know, you've got X16, X8, and then also these M.2 slots. I'm not sure why you'd want a hardware method of disabling the M.2 devices. But for the GPUs, it's actually a very simple reason. If you're running a multi-GPU setup and you don't feel like pulling one of the GPUs out, either because it's on a water block or because it's on a liquid nitrogen, and you're troubleshooting something, or you just want to run single GPU instead of dual GPU, well, you can use this this switch over here to just disable the second card, which is misbehaving or you just don't want to use. So yeah, that's what that's for. And then over here, we have a slow mode switch, which basically allows you to drop the CPU frequency to the lowest ratios with just the flick of the switch. Now, at ambient, this is basically pointless, but on liquid nitrogen, this is really great for conserving nitrogen, because you don't really want to be sitting on the desktop at 6 gigahertz if you don't have to. And also, well, that's most of it really, is like if you don't want to be sitting on the desktop at 6 gigahertz, you don't have to with this. You can be sitting on the desktop at at like 1.2 or something. Like it's a really low frequency, and that significantly reduces the heat output of the CPU. It also makes it less likely for the CPU to crash. So if you're like, saving a score and moving it to your USB stick or just pulling some file from your USB stick or whatever, you need to fix something in the OS, that kind of thing, you can do that with slow mode enabled and not have to worry about the system just burning through liquid nitrogen like no tomorrow, which, a 10-core CPU locked at 6 gigahertz can actually do quite easily. Yeah, that's what that's for. And then over here, we do have a kind of neat feature for extreme overclockers, which is that, and I've not checked which specific SATA ports it is. I think it's these two at the top. Basically, there's an AS Media SATA controller, so you get 2 extra SATA ports, but the main reason we have this AS Media SATA controller is that it's actually Windows XP compatible, and there's a bunch of benchmarks that just run way better on Windows XP than they do on any other operating system. And so, or at least any other Windows operating system. The thing is, for competitive overclocking, Linux is not supported. So you're kind of stuck running various Windows versions. And for some of the old benchmarks, Windows XP is just faster. And Windows XP does not appreciate modern SATA ports. So there's a sort of Windows XP compatible set of SATA ports on this motherboard, which is pretty neat. If you're going to be running benchmarks like W Prime and SuperPi, and I think PiFast as well. And there might be a few others, but I don't really do a lot of these really old benchmarks. And I also don't usually use Windows XP, so I'm not sure which ones it would be. I think some of the old 3D marks also fall into that category. Anyway, we've got color-coded front panel headers, which I'm actually a big fan of, though, you shouldn't be putting this motherboard in a case. But if you are, like, the color coding makes life a lot easier. And there is a beeper on the motherboard, so it will beep at you when it boots up. And you can, of course, turn it off, but it is quite annoying if you don't. And then we have a 6-pin power connector over here for extra PCIe slot power. I'm not entirely sure why you would need that, as 2 GPUs shouldn't really be able to overload a 24-pin unless you're doing horrible things to their like 12-volt power distribution. So, yeah, but it's there, and it doesn't hurt anything by being there. Also, there's a bunch of LEDs along the various PCIe slots, like you can sort of see them over here. And you can see them over here to indicate which PCIe slots are active and if there's anything in them. So also, helps you figure out if you, I guess the main idea behind those LEDs is so that you don't forget if you've, disabled PCIe slots using the dip switch over here. So, yeah, that covers most of the actually all of the overclocking features on the, overclocking specific features on this motherboard. And as far as I'm concerned, you've got your triple BIOS, you've got a safe boot. It's not necessarily the most reliable safe boot ever, but it is better than nothing. A lot better than nothing. And honestly, with my past uses of dark motherboards, I've not had an issue, I've not had major issues with the safe boot function. I have had situations where, it's I get into the BIOS, but the memory settings are so unstable that it does, we can't actually do anything. But it's not a frequent occurrence. So, the safe boot button serves its purpose of getting you into the BIOS when you're when you screw up, without having to reset all your settings. So if you're like me and really forgetful when it comes to saving profiles, well, you're not going to get screwed over by that. The postcode monitoring thing is cool, though I consider, it's not really something I use a lot, but it is a cool feature to have. We do have BIOS flashback. We've got basically everything you would really want from a overclocking motherboard. And then, of course, we do have I guess at this point, let's move on to the memory topology. We're going kind of out of order. VRM's going last. So yeah, let's talk about the memory. So of course, this is a 1 DIMM per channel motherboard because extra DIMM slots add extra length to your traces and extra interference and extra parasitics, and nobody likes any of those. So 1 DIMM per channel it is. The board is really solid with Samsung B-die memory chips, both in single rank and dual rank configurations. So, 2x8 and 2x16. It also works really well with Micron Rev B memory chips. Rev E is probably a bad idea because Rev E has very Rev E has very specific termination resistance requirements, and most you can technically get it to work. It just takes a lot of effort. So I wouldn't really recommend running Micron Rev E based memory kits on this motherboard. And my experience with running Hynix DJR on this board has been fine. Then again, I don't know why I would stick Hynix DJR into a board like this. Hynix DJR is just a very mediocre IC, if you ask me. Like, if you care about performance, either get, because the thing is, let's say you wanted 64 gigs of RAM, you can get Micron Rev B for that. In dual rank, it'll run great. If you want 32 gigs of RAM, you have the option of single rank Rev B Microns or dual rank Samsung B die. Both of those are, the Samsung B die is going to be more performance per clock, harder to overclock though. And the single rank Micron is going to be, a bit slower, actually probably quite a bit slower, but much easier to work with. And then for single rank B die, I mean, it's just single rank B die with, it's pretty normal stuff to run. So yeah, that's kind of the ICs I would run on this. In terms of the memory overclocking, this board trains insanely fast. Like, this thing boots so quickly, it's ridiculous how quickly this board is able to train. So yeah, that's had me really, really impressed. And I was supposed to talk about the topology here, and we got kind of off track. So yeah, 1 DIMM per channel basically means you can run anything from 16 gigs up to, actually you could run 8 gig, 2x4 as well, but I don't know why you'd want to do that, but you could. But realistically, you can go from 16 gigs up to 64 gigs, and there's plenty of high performance options in those capacities, even for just 2 DIMM slots. So I really don't I don't see any, there's no downsides to this. Even for a daily system, I really don't see any downsides to only having 2 DIMM slots right now, because there are 16 gigabit ICs. So as long as you don't need more than 64 gigs of RAM, you're fine. So that's kind of that. And then this is a shielded, topology. We can't see any memory traces on the top layer or the back layer. That's not the back of the board. Oops. That's the back of the board. So yeah, you can see that we have full sort of ground shields over here. And then in this area, so full ground shield like this. So that's all ground in that area. And this is where you have all of your sort of data traces for your memory sticks. And then down the middle, you actually have the memory power plane. So this is all VDIMM. And the reason this is done is because I think it's the command address bus that runs through this area is actually supposed to be referenced against the memory voltage rather than against ground. So that's why you have that VDIMM power plane running through that area. Also because your memory VRM's right there. But even if you have, there are some other boards that would have, the memory VRM, say, over here relative to the DIMM slots, and those end up just doing that anyway. So, this is how it's supposed to look, basically. Though we do see some other boards, say from Gigabyte, where they just put a ground shield over absolutely everything. But those boards will still have an internal VDIMM plane in the middle of the DIMM slots. You need that there because that's your power distribution for the memory controller and the memory slots. So it's going to be so this is going to be somewhere. It's not necessarily on the top layer though. Or not necessarily on the top and bottom layers like we see here, but it is going to be present on, you're going to see that basically on every motherboard one way or another. And yeah, so it's kind of interesting. So the previous dark boards actually weren't shielded. They were 1 DIMM per channel still, but we weren't seeing any of this shielding. I don't know how much that has improved memory overclocking because, I don't have a Z490 to compare against. And then also a lot of it comes down to BIOS optimizations. So depending on, how much work went into supporting 10th gen or 11th gen on this board. I've only tested this board with 11th gen so far. It'll sort of change, you wouldn't necessarily be able to tell if there's a overall topology improvement unless the BIOSes are exactly the same in terms of optimization level. Yeah, with 11th gen, this board is just incredibly fast to train. So that's really, really cool. And then we've also got SMT DIMM slots, which are just a further, way of minimizing the parasitics of the memory slots, as you don't have pins going through all the way through the board. So yeah, that's what's going on with that. And at least for 11th gen, I've been really, really impressed with the memory overclocking on this board. Like, it is, especially with Samsung B-Die, it is really good. So yeah, good job EVGA on that. And now let's talk about the power delivery. So the main VRM, or oops, I'm trying to highlight the capacitors, which I don't do on the principle of like it's hard to like you'd have to like justify why you choose certain capacitors and don't others. So instead, I just don't cover any capacitors. The power like, it's kind of awkward because like you have, let's just cover this one first, I guess. So this over here is VCCIO. Is it? Yeah, VCCIO. This over here is, of course, your memory VRM. So that's your input filtering inductor, input filtering capacitor, output inductor, and there's your power stage. So that's our VDIM or VDDR. Actually, I'm going to go with VDDR for today. That is not a D there. VDDR. Then over here we have VCCIO2. So that's new voltage rail for 11th gen. This powers the PCIe and memory controller. And this is a critical rail for memory overclocking. Like, that's like, you basically don't have to touch VCCIO at all. It's all about VCCIO2 for high memory speeds, as well as VCCSA to some extent. So speaking of VCCSA, that is located over here. There's like, the funny thing with these is they're not really hard in terms of power delivery requirements. They're just like, they have to be present. So yeah, that's where they all are. Then we've got VCCSA over there, and then all of this is VCore. And the VCore VRM on this board is, and then up here we do have an iGPU phase. So if for some reason you want to use the integrated graphics of your 11th gen CPU, you can. I don't know why you'd want to do that, but you do have the option. So anyway, the VCore VRM on this board, well, so VCore, iGPU, and VCCSA are all controlled by this chip over here. That chip is an ISL 69269. So this is a up to 12-phase voltage controller. Here it is running in an 8+1+1 configuration. So +1 for VCCSA, +1 for iGPU, and then VCore is an 8-phase it's an 8-phase VRM. So you have 8 PWM signals that go from the ISL 69269 to these chips, and there's 8 of those. So yeah, those 8 chips. Those are all ISL 6617s. And these are doublers with the option to not double, which is actually what this board is doing here. So this is actually 16 power stages running in 8-phase mode. It's not a 16-phase because the ISL 6617s are running in synchronized mode. The reason why you would run them in synchronized mode is very simple. It gives you better transient response, and you do still get a slight efficiency advantage with with having ISL 6617s running in synchronized mode compared to just running a PWM signal straight into 2 power stages at the same time, because the ISL 6617, even in synchronized mode, can do some amount of current balancing between the 2 power stages, so it can optimize the make sure that all the current is being handled evenly by all the power stages instead of like one power stage handling significantly more current than the other ones, which would lead to, well, worse efficiency because your power losses in, like, a large part of your power losses in power stages is I squared R. So if there's a slight current imbalance between your 2 power stages, you do actually lose efficiency for that. So even if the overall current output is the same, like if it's not properly distributed between the power stages, you're not gonna be getting the maximum efficiency out of your power stages. So here's a page of the ISL 6617 datasheet to sort of explain what's going on with this VRM. So basically, so Intersil in their datasheet, this is for a 6-phase design. So you have like 24, so you could think of this as like 24 power stages, 24 inductors, but only 6-phase operation, which this isn't. This is more like having 24 channels with, well, no, I screwed this up. Well, anyway, so here's the like efficiency difference. That's the main thing I wanted to show, right? Like, so this is if you didn't have any doublers whatsoever. This is if you have the doublers, but they're running in synchronized mode, so you don't actually get extra phases. You just get sort of better current balancing between your parallel power stages with the, well, it's not really, you don't really get like better transient response compared to just a VRM without the doublers. In fact, they add a little bit of, a very small amount of delay to your PWM signals, so it actually makes the transient response ever so slightly worse. But it's much better transient response than if you were running actual 16-phase mode with the interleaving, because you get better current slew rates. But anyway, and then here you would have phase doubler in interleaving mode, which gives you like the highest possible level of efficiency, but also not the best transient response. So that's why, especially on a lot of actually most modern motherboards that use ISL 6617s, run them in synchronous mode, not doubling mode, because the efficiency of the power stages is already really, really high. And so the downsides of just, like not going from here to here just doesn't matter that much compared to the benefits that you get in transient response by just running the power stages running the doublers in synchronized mode, and so running the power stage, like switching the two power stages on and off at the same time. And yeah, and here we can see some sort of like ripple reduction, but the thing is, well, you can see how there's diminishing returns, right? So once you're up at 8 phases, the improvements in ripple current going from 8 to 16 are not really that relevant. And it's far easier to deal with. Like the other thing is your ripple current from the VR, like the ripple created by the VRM itself is just kind of irrelevant compared to the actual transient loading produced by the CPU. As the CPU can very quickly go from pulling, 10 amps to 100 amps or 200 amps, like crazy high, large current swings very, very quickly in the matter of like fractions of a millisecond. Even less than that. Like, so the ripple current of a VRM is just kind of like basically irrelevant. Like all of these output filtering capacitors here, they're not really there to deal with the ripple current from the VRM, though they do that. But that's not the reason why you have this many of them. You could use far fewer if the only thing you needed to do was deal with the ripple current of the VRM. No, this is here to deal with the transient loading created by the CPU, and the same goes for the input filtering capacitors, which we basically have one per phase. As you can see, there's, 8 of these like large 16-volt capacitors on the 12-volt power plane. And then on the back of the board, for the actual like turn-on transient of each power stage, you have multilayer ceramics directly behind each power stage, as well as, do we have a couple around them on the top side? Not really. I think most of these are just like bootstrap and stuff, though this might be for 12 volts. So, yeah. Anyway, so this is not a 16-phase. It's also not a 21-phase because EVGA has probably the worst method of advertising VRM phases of any motherboard manufacturer, because they basically go and just add up like, the way EVGA arrived at the 21-phase label on their website is, okay, so you've got 1 phase of VCCIO, 2 phases with VCCSA, 3 phases with iGPU, 4 phases with VCCI, like regular VCCIO, 5 phases with VDDR, and then we have 16 phases from the vCore VRM, and therefore we have a 21-phase VRM, and it's like, no. Those are totally separate voltage regulators. They're not, this is not a 21-phase VRM. This is, like, yes, technically there's 21, it's not really even 21 different phases because those doublers are in synchronized mode, so you only have 8 phases of vCore. But anyway, like, which isn't a problem. Like, this is completely fine. Like, the thing is, the phase count of the VRM is a method to achieve certain performance targets. It's not in and of itself a design goal. Right? Like if you can get the performance you need with less phases, why would you get more phases? So yeah, which is why basically everybody runs ISL 6617s in synchronized mode these days because, yep, they slightly improve your efficiency, but transient response is far more important than slightly reducing your steady state ripple when, how often is your CPU actually at steady state? Not very often because Windows keeps waking it up or interrupting it depending on what it's doing at the time. So yeah, that's sort of what's going on with that. So VCore here is a 8-phase with 16 power stages in it with per power stage current balancing. Thanks to the ISL 6617 still, doing that to improve the efficiency. But this is very much not a 21-phase. So, but it's still a really, really great VRM. And in terms of current handling capacity, it's like at the top of what you can get. Well, it's like, the thing is, we have Z590 motherboards with 20 power stages on them now, which I think is completely stupidly excessive for VCore, like just for VCore, right? Like that's the thing is like the reason I think EVGA added up all the different voltage regulators and was like, we've got 21 phases is because like MSI has a VCore VRM that literally has 20 power stages in it. With actually 20 phases, because somehow they got Renesas to build a 20-phase controller, or more like Renesas now makes a 20-phase controller. I still don't know why. I think the reason that 20-phase controller exists is it's supposed to like power multiple different voltage regulators with high phase counts. It's not meant to be used as a 20 plus 0. It's meant for like a 10 plus 10 or something. But MSI used it as a 20 plus 0. So EVGA's phase like power stage and phase count here looks kind of low, but in terms of actual current handling capacity, like it really isn't. Since the power stages EVGA is using are ISL 99390s, and these are 90 amp smart power stages, so they are ridiculously efficient. In fact, these are some of the most efficient power stages you can get right now. I think there's some from Texas. International Rectifier has some power stages that might technically be slightly more efficient, though the issue is also comparing data sheets between different manufacturers doesn't really work that great because they don't all use the same testing methodologies. So that gets really awkward. But anyway, with 16 of these 90 amp smart power stages, this VRM has no problem powering anything that you could put in this socket. In fact, it's well into the territory of VRMs that don't really require a heatsink, which we'll get to in the late. Like we'll get to the VRM cooling that EVGA has opted for because I have some very strong opinions on it. So anyway, VCore is insanely powerful. It's capable of outputting 200 amps of current while producing only around 15 watts of heat on the power stages themselves. That's not accounting for power losses in the actual power plane, though. Should mostly cover the inductors because the inductors don't generally have that much resistance. Like they are a really thick piece of wire going through a bit of metal, so these compared to the power plane, these generally don't have that much resistance. And also, this is a 10-layer PCB, so the power plane on this should actually be also very low resistance, just because the board's got a lot of layers. And well, in this area of the board, there's not really much else than the actual power delivery for the CPU that you need to route. Unless they're running PCIe lanes like that, which would be really awful. Like, that's a big part of why your VRM normally goes up here and here instead of, between the CPU and the PCIe slots. But I'm pretty sure it really looks like they're running the PCIe slots, PCIe lanes around, which that's sort of the way it should be. Like, that's how you'd want to do that. Because the VRM is actually very noisy. Thanks to all of the, electromagnetically noisy, as in the switching of the power stages, and I don't mean that in it's putting a lot of switching noise. Well, it does put a lot of switching noise on the 12-volt power plane, but that's what we have the capacitors for. No, the actual switching act of the power stages itself causes EMI with near to the VRM. So you don't really want to be running sensitive signals past your switch nodes of the power stages, which is the connection between the output of the power stage and the inductor. Don't really want to put anything sensitive anywhere near that, so yeah, the PCIe has to go around. Probably a big part of why this board has 10 layers is just so that they can get everything to avoid the VRM, which is now in the middle of the board. Anyway, yeah, so 200 amps output, the VRM will produce about 15 watts of heat. Then 300 amps output, it'll produce about 23 watts of heat. 400 amps, because, you know, this is a motherboard that you would want to run on LN2. 34 watts of heat. Again, you know, not accounting for power plane power losses. 500 amps, about 48 watts of heat. And 600 amps, it would produce about 66 watts of heat. So, yeah, like, this is right up there with, well, a lot of other like, the thing is, this is not like a unique number of phases to see on a motherboard. 16 power stage V-Core VRMs. I mean, I think the Z490 Unify had that. The Z590 Unify probably has that. Gigabyte has, I think, an 18 power stage V-Core on the Master and a 16 power stage V-Core on the Ultra, maybe. So, like, this isn't a unique VRM in terms of how many power stages it has and what power stages it's using, but also, like, there's really no reason to go much above this. Like, any CPU you can put in this socket is going to be, you know, isn't going to require any real effort from this VRM to power. This is more than enough for, like, literally any application that you could, you know, use this motherboard for. So the VRM, like, it's not the most overkill VRM to ever be on a Z590 motherboard, but that's like, I'd say that's mostly because MSI and Gigabyte have gotten very unreasonable about what they've put on their top-end boards. This isn't sort of like, oh, this is like a reasonable design. No. This is still very overkill. It's just not, you know, quite on the same level as some of the other boards out there, which is fine. We don't need 20 power stages. There really is no reason to go that far. And also, I far more prefer what EVGA has actually done with the output filtering here compared to everybody else, because these are SP caps. So the reason I'm so excited about these is that SP caps are molded aluminum polymer capacitors from Panasonic. And these are the 2.5 volt variant, which is even better, because technically the MSI Z590 Godlike does use SP caps for its output filtering, but they're 4 volt SP caps, and you can't get those in the super low ESRs that you can get for the 2.5 volt ones. Depending on which exact, like, I'm not sure which exact parts EVGA is using here, but basically, if you want the lowest possible ESRs and lowest possible ESLs that, like, an aluminum polymer capacitor can have, they're these. Like, 2.5 volt, 2 and 2.5 volt SP caps are as good as it gets for molded polymer, molded aluminum polymer capacitors. Like, in the past, EVGA actually, on, say, the Z490 Dark, they actually used tantalum polymers, which are worse, which is probably why they switched over to the SP caps on the Z590 Dark. On the Z390 Dark, they also used tantalum polymers. Again, they ditched those. So, like, in terms of the capacitor selection on the output here, this is as good as it gets. There's literally no better bulk capacitor than 2.5 volt SP caps, at least as far as I'm aware. And you do need the 2.5 volt rating, because if you're running CPUs on LN2, you can get up to some seriously high voltages, and so the 2 volt capacitors wouldn't really be ideal for that. And then also because, you know, yes, we have these super low ESR, super low ESL SP caps, but they're still worse than your multi-layer ceramics, and so EVGA also has a bunch of multi-layer ceramics mixed into the output filter outside the actual socket, because there's a lot of motherboard, like, there's a couple motherboards that we have these days that, like, have molded SMD capacitors like this for their output filtering because of the ESR and ESL benefits, but they won't necessarily start adding also more multi-layer ceramics than what you can physically fit inside the CPU socket cavity. So I'm a huge fan of the output filter that EVGA has put on this board. And then on the back of the board, like, we've got more SP caps in the socket, like all of the capacitance. So yeah, like, and then we also have more multi-layer ceramics, like, right along the edge of the VRM as well. So, like, as far as output filter, as far as output filtering goes, and that's the important side of the VRM. Like, there are some motherboards that will have, like, tantalum capacitors for the input filter, but that's the input filter. It doesn't need to be super fast. Through-hole capacitors like these Nichicon FP series caps are perfectly fine for that. And then on the output, that's where you want to go with the really, really fast, low ESR, low ESL, molded polymers, and then, of course, your multi-layer ceramics. Though you do still need some multi-layer ceramics on the input because of the initial turn-on transient for any power stage, which is why these exist. But yeah, like, I love the filtering configuration on this motherboard. Like, this is it. Like, everybody needs to do this. So, yeah, now, if there's gonna, like, I've not yet taken oscilloscope measurements of this board, but at least on paper, this should have the best voltage regulation of any Z590 motherboard because of the capacitor selection that EVGA has gone for. And for comparison, for the Z390 motherboards that I tested, like the Z390 Dark was the best voltage regulation Z390 board that I ever tested. Though at this point, I feel like Gigabyte has now done the Z590 Tachyon has all tantalum output filtering, which should still be slightly worse than this, just because tantalums are inferior to molded aluminum polymers in terms of both ESR and ESL. And then also the Tachyon doesn't mix in a bunch of extra multi-layer ceramics to its output filter. Yeah, like ultimately, like as much as I'm a fan of this, because this is the best configuration of capacitors you could go for, at least with as far as I'm aware. There's a decent chance this doesn't make a measurable difference when we ask the when I go to test this with the oscilloscope. But if there's any motherboard that like should have the best voltage regulation, it's this one. There's also a chance that my oscilloscope's not sensitive enough to measure the difference, but yeah. The thing is, like, at the end of the day, you do hit the limit of the actual CPU socket at some point. So that's kind of the main concern is, like, because I do take my oscilloscope measurements from the actual CPU package. I don't take it from the motherboard. So if you tested this motherboard from, like, say, a capacitor inside the CPU socket cavity, this should really be way better than any other motherboard out there. Whereas if you tested it at the CPU, well, that's after the impedance of the actual socket. And if that's high enough, then that could actually negate all of the benefit of all these capacitors, which would kind of suck because that would basically mean that we have hit the limit for what's possible in terms of, power delivery for LGA 1200 CPUs. But yeah, we'll have to see about that when I actually get to measuring that. But at least on paper, this is my favorite like VRM on any Z590 motherboard. We've got tons of power handling capacity, and then the best capacitors in the places they most matter. So yeah, like this is it. As far as VRMs go, this is it. And the thing is, like EVGA also use those same SP caps for VCCIO and VCCIO2 and VCCSA. Like they just use them everywhere for output filtering, except for the memory, because the thing is you can't really, like for the memory you need higher voltages, and also the memory is actually really not that heavy in terms of transient loading. So the memory uses regular, FP series capacitors from Nichicon, which are through-hole capacitors. But like all of the important power rails, they get SP caps. Though I really don't think it makes much of a difference on things like VCCIO and VCCSA and, VCCIO2 and VCCIO, because like those are all relatively low current rails that I've admittedly never checked, but they don't push that much power. They really shouldn't be, heavily shouldn't be experiencing heavy transient loading like the vCore VRM does. And technically the iGPU VRM also experiences a lot of transient loading, but if you're actually using an iGPU on a Z590 Dark, I think you've got bigger problems to solve. Not that there would be any issues. We've got SP caps for that as well, because of course we do. So yeah, huge fan of the VRM and just everything about it. And yeah, out of the dark, like it's cool to see the progression, in my opinion, on the darks though. Like, because the Z390 Dark started with like all tantalum output filtering, like all the bulk capacitors of the output filter were tantalum. Then with the Z490, they added some SP caps into the socket. With the Z590, they've just replaced all of the tantalums with SP caps, which, yeah, like that's a totally sensible progression right there, because the SP caps are just better. And I've both from the documentation and my anecdotal experimental experience with cap modding GPUs, basically I got sold on SP caps when I soldered a couple of them to a GPU that so far hadn't seen any improvement from any other cap mod, and then it suddenly picked up I think 20 megahertz worth of core clock, which really isn't much, but that's kind of what you'd expect with a small improvement with in voltage regulation that I just wasn't getting out of the same number of tantalum capacitors or through-hole capacitors or any other capacitors that I was testing at the time. None of them really did anything, and then I got to testing the Panasonic 2.5 volt SP caps, which I paid I think $20 for, and they just way better. They actually made a difference. So that's sort of, yeah, these, not the specs say they're better, and in my experience, they actually very much are better. Probably a big part of why we see them on a lot of high-end GPUs as well. Anyway, so yeah, that's enough about the output filter, I guess, and the VRM in general is just really great VRM on this board. And now let's talk about the VRM heatsink, which it's made of copper. And to most people, that would be a good thing, because copper is a better heatsink material than aluminum. Except it makes the board way more expensive than it has to be. We have a VRM that barely needs a heatsink in the first place. And, yeah, it's just, this right here is, I don't like it. It's really that simple. I don't like the copper heatsink, because it just makes no functional difference to this board. It just makes it more expensive. This board is, I think, one of the most expensive overclocking focused Z590 boards there are. And a big chunk of that is going to be this heatsink. I wouldn't be surprised if by removing this, if EVGA replaced the copper with aluminum, they could have easily probably cut the price of the retail price of the board by $50, if not more than that. And to me, that's just kind of you know what? If I could have the board for $50 less, obviously I didn't pay for it. I have it as a review sample, but if I was paying for it, I'd rather get it with an aluminum heatsink for $50 less. In fact, I would prefer if there was no heat. Honestly, they could have shipped it with no heatsink, and I would have not cared, because, the VRM is what it is. And admittedly, you probably would want some kind of heatsink, but this right here is just so unnecessary. And the thing is, if you're going to run this board on liquid nitrogen, you're actually going to ditch that VRM heatsink anyway, because it's made of copper. It's a massive condensation magnet. If you get any water on it, a droplet of condensation just falls on it, or some of the ice that forms on your LN2 pot just gets picked up by the fan and then drops onto the VRM heatsink. It's copper. It's going to corrode. It's going to be absolute, if you're in a high humidity environment, this heatsink is going to look disgusting in a year or two. Copper is just totally, especially for a VRM, this heatsink would probably be adequate for cooling a CPU. Not very well, but yeah. So, I'm not a fan of the heatsink. And then not only did they, just drive up the manufacturing cost of the VRM heatsink by using copper, which is way more expensive than aluminum for negligible performance gains, they strapped fans to the damn thing. Also, I have no idea where this fan is supposed to get airflow, because there's 2 LAN ports right next to it. That thing has, I guess they expect all the air to just get squeezed through this gap between the 2 LAN ports, which is just get rid of the damn fan. Why is at least EVGA, unlike some other motherboard vendors, doesn't use a proprietary header for the VRM fans. So if you want to ditch the unnecessary VRM fans, you get an extra fan header on your motherboard. But why is this a thing? Why do motherboards now have freaking fans in the VRM? No. Like, and then also, why is the VRM heatsink made out of copper? Like, just, and you could argue that the SP caps everywhere are an unnecessary expense, considering that ultimately they're going to be limited by the impedance. Like, there's a decent chance they're going to be limited by the impedance of the CPU socket itself. But the copper freaking heatsink is just like, no, no. Also, if you're on LN2, you're like going to want to remove it, and then it removes your chipset heatsink because it's connected to the chipset heatsink with a heat pipe. So then you need to go figure out a cooling solution for your chipset. Not that like it really needs it that much, but I prefer to have a heatsink on the chipset, even if it doesn't technically require it. And then you might be like, yeah, but the VRM doesn't technically require a heatsink either. Yes, which is why I said aluminum heatsink. That would have been the preferred option, is just like a nice, simple aluminum heatsink. And if they wanted the copper heatsink because it looks cool, you could just anodize the aluminum to look like copper. Most people can't tell the difference. Yeah. Like, just anodize an aluminum heatsink to look like copper if it's a visual thing, and if it's not a visual thing, then just have an aluminum heatsink. It would make the board more affordable. Which I think, especially if you're EVGA, where you're making two motherboards, you're making a Z590 FTW and you're making a Z590 Dark, like, why would you want to, price out your potential customer base by putting an unnecessary copper heatsink onto your motherboard? It doesn't do anything. It's just an unnecessary expense as far as I'm concerned. And there's so many other overclocking focused Z590 boards that it's like on Z390, EVGA didn't really have a lot of competition for a 2-DIMM overclocking focused motherboard, right? Like, you could get the Apex that Asus wasn't really selling to anybody, and you could get the Dark, and that was kind of it. And then similar on Z4, and then on Z490, you could get the Maximus 12 Apex, which was far easier to get than the Maximus 11 Apex. Or you could get the Z490 Dark, and that was sort of your two options for extreme overclocking focused Z490 boards. And then for Z590, like, we've got a Tachyon, we've got an Apex, we've got an OC Formula, we've got a Unify X, we've got a Dark. There's there's 4 other boards that this is trying to compete with, and this is the most expensive one. And a big chunk of that price is probably that copper heatsink, and it does nothing. So I really don't like that copper heatsink. Like, I think this is just why. Especially now, like, when raw material prices are going up and up and up. It's like, of all the times you could put a copper heatsink on your motherboard, why now? Like, if copper was like incredibly cheap or something, then okay, fine, use it. Like, that's the main reason we don't regularly use copper for heatsinks, is because it's way more expensive than aluminum. But right now, why would you use copper? So yeah, I'm really not a fan of the VRM heatsink on this, because, like, yes, it's a really, really good heatsink. It's going to keep the VRM incredibly cool, but a simple aluminum heatsink would have done that too, because the VRM is really efficient to begin with. So yeah, that's kind of the thing, is that this right here is just like, it doesn't make the board worse, but it does make the board more expensive. And like, I'd prefer, like, if I was buying this board, I'd prefer to pay less money. Thank you very much. So anyway, yeah, that's the Z590 Dark, an incredible motherboard with a totally unnecessary VRM heatsink. To like the highest degree unnecessary heatsink. Like, we have a lot of motherboards where I complain that the heatsink is unnecessarily overkill. But this board takes that to a whole new level, because most of the other motherboards, they the other vendors, they contain themselves. They just stick to aluminum, because sure, the heatsink is huge and excessive, and there's fans in it for reasons no one can explain, but at least it's still made out of a cheap material. And then EVGA is over here, like, okay, so most vendors will stick like a fan into their heatsink. We're going to stick 2, and then we're going to make it out of copper, because it wasn't expensive enough to begin with. So yeah, but amazing board, especially with 11th gen CPUs. I've not tested it with 10th gen yet, but with 11th gen, the memory overclocking on this board is amazing. I expect on the oscilloscope, this is just gonna, like, this is either gonna tie with all of the boards that I've tested so far, because the transient response testing that I've done so far on LGA 1200 has basically been a lot of boards performing exactly the same. So that's where I sort of suspect that the socket is already starting to limit the voltage regulation performance of the motherboards. But, you know, there's two boards that I still haven't, like, there's this and the Tachyon, which I still need to test, and one of these has to, like, be an improvement, because these really do go all out in terms of the output filtering configuration, especially the dark. Like, SP cap, 2.5 volt SP caps, not the 4 volt ones, 2.5 volt SP caps, and then all the extra multi-layer ceramics, like, yeah, so there. That's it for the video. Yeah, thank you for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. If you'd like to support what I do here with actually hardcore overclocking, I have a Patreon. There's a link to that down in the description below. There's also the AHOC Teespring store, where you can pick up shirts, stickers, posters, you know, the usual YouTuber merch. It would be much appreciated if you'd, you know, check out the Patreon or the Teespring, as they do help out immensely with running the channel. And yeah, that's it for the video. So thank you for watching, and goodbye.